Hey Chase,
Hello.
how you doing today?
Hello. I'm tired. I'm
Yeah?
hungry. I had to wake up to teach this morning, and I've been teaching all the way till now.
What do you teach?
I'm a martial arts instructor.
How are you? Sounds fun.
It can be,
Mm-hmm.
but it's very tiring and sore.
Yeah,
I, uh,
bet.
yeah.
Do you teach at a
I have I don't own it, obviously, but
is
I
that what a
have students.
dojo is? A dojo
Yeah,
word I'm trying to think of?
it's called a dojo, yeah.
Okay.
I guess, I teach at one of those.
Uh-huh.
Not like, yeah,
Okay.
teach the young, new kids.
Uh-huh. All right. So looks like we're working on 5.1, 5.2, and 5.4.
I don't expect us to get through all of these because I know it's a lot, but I'd like to at least cover the concepts of 5.1 and 5.2 and then get to 5.4 if possible.
Why did they skip 5.3? I'm curious.
I have no idea.
Actually, I do have an idea. 5.3 is one of the toughest parts about calculus. Looking at the derivatives of inverse functions. It's interesting that they skipped it. Well, a lot of them do. I'd say I only come across about 1 out of every 5 calculus students that does 5.3. All right, so which of these do we want to do?
This is 5.1.
Uh-huh.
For 5.1 we want to look at, let me get it up real quick.
What's that?
So I was opening it up real quick. I was going to include it in the email this morning, but I was in a hurry to get to the dojo on time.
Okay.
Here's the question she has posted for 5.1.
Okay. Oh, I see. Okay. 7 through 10? Am I reading that right?
Yeah.
All right. I had my window closed down, so I didn't see that at first. Good. I didn't want to do 1. Now my computer's hung up. That's nice. Hold on. We may have to wait a second here.
I'll be right back. I'm going to stand and grab something to drink. I haven't.
Okay, good. That's a good time to do it. I may have to reboot, but I'll let you know when you get back.
Okay. Be right back. Okay, so
I'm going to run Task Manager here and close out this document. See if that'll save me from having to reboot it. It might have. Okay, let me reopen the document. And you said 7. Okay, so let's match the functions with the graphs. Number 7 is natural log of x plus 1. Which graph is that?
number 7, natural log of x plus 1.
Here I will graph the natural log elementary function for you. Looks like this. And
Wouldn't that be a?
goes through this point 1 comma 0. So this is y equal natural log of x. Notice that the plus 1 is a vertical shift, not a horizontal shift.
Well, then it would be b.
Correct. And b is this function that's been shifted up 1. Notice that that point right there is 1 comma 1 instead of 1 comma 0.
Yeah.
Okay. How about 8?
8.
minus log x.
The negative log x would be, do we have this?
It's a reflection about which axis?
The y-axis?
No, the x.
The x?
Yeah, let me show you a way to remember that. Y equal x squared, right?
Yes.
Well, y equals, if I stick the negative sign in front of the function, it just means that every point that's here would be down here, right? So it has to be a reflection across the x-axis. If y, in other words, if you're looking at minus f of x, which we are. When I say minus natural log x, I'm looking at the negative of the function, which means I'm going to reflect it across the x-axis, not the y-axis. So which graph is it? So I look at my natural log function, which is right here, and reflect that across the x-axis.
That would be D then.
Okay. Number 9. Number 9 is what kind of a translation?
X minus 1. That doesn't that just shift it?
Yeah, that's the same thing as f of x minus h, where in this case h is 1. So, in other words, if this function right here, if I call that f of x, the natural log function, that's my elementary function, and if f of x minus h is a horizontal translation, then the function we are looking at is f of x minus 1, which would be natural log of x minus 1. So we are looking at a function that has been translated to the right because h is positive. When h is positive, it's a translation to the right. When it's negative, it's to the left. So there's our function that's been moved 1 unit to the right. Notice the vertical asymptote has been moved 1 unit to the right.
Yeah.
It's easier to see this one than it is to see a vertical shift. When you do a vertical shift on this, it's not that noticeable. In other words, this looks very similar to what I've drawn. But when you do a horizontal shift, the entire asymptote moves. And finally, 10, when the negative sign is inside the function, you have a reflection across the y-axis. So we're going to have a double reflection here. We've got a reflection across the y-axis because of that, and a reflection across the x-axis because of that. Well, if I blow this up and figure out what that looks like, well, the first reflection looks like that. The second reflection looks like that. So whatever looks like that is what we're looking for, which is C. Okay? And 13. Sketch the graph of the function and state its domain. This is kind of interesting that this is not really calculus here. This is pre-calc. So if f of x equals natural log of 2x, how does that graph? What's the impact of that 2? In other words, if our natural log function looks like that, going through that point, 1, 0. So this is natural log, that's y equal natural log of x. So when we put the 2 next to the x instead of in front of the function, what's the consequences?
Does it make it twice as drastic? Like,
Well, if you put the 2 in front there, it's a vertical stretch by a factor of 2. If you put the 2 in front of the x, it is a horizontal shrink by a factor of 2.
yeah.
Notice that when this number is greater than 1, it's a horizontal shrink. If this number is greater than 1, it's a vertical stretch. They kind of have the opposite effect, although it's actually the same effect. In other words, if I were to do a vertical stretch of this, it's going to look very similar to a horizontal shrink. Well, the one thing I know about the horizontal shrink is it's got to go through that point right there, which is 1/2, 0. So the curve we're looking for is that. That's been horizontally shrunk. In other words, pushed together, which you'll notice has a similar effect, not exactly the same, but a similar effect to a vertical stretch.
Okay.
It's worth, just because we're doing this, let me do something here. It's going to make this maybe a little more understandable. There's only 6 things you can do to a function. If that's my function. Let's talk about the things you can do vertically. Well, if I do c times f of x, which would be c times log x, where c is any constant, that is a vertical stretch shrink, right?
Yeah.
If I do a vertical shift, that is f of x plus c. In other words, log of x plus some number.
Okay.
Horizontally, let's talk about a horizontal stretch or shift, or shrink rather. Well, that is f of c times x, which in this case would be log of cx. And that is a horizontal stretch or shrink. The other horizontal translation is a horizontal shift, which is f of x minus h, which would be log of x minus c. So those are your 4 basics. And the only other 2 are the reflections. Reflection on x is negative f of x, or in this example it would be negative log x. Reflection on y-axis is f of negative x, which would be log of negative x. Those are the 6 things you can do. And this is the best way to look at it. In other words, using the f of x designation as opposed to the y designation allows you to describe each of these 6 things as a function of something being done to f of x. All right?
Yeah.
So there's a lesson on the material that they're going over here. In other words, they're asking us what all of these shifts are doing and stuff. So we did 13, so let's do 15. Hold on a second. Let me get to the bottom of my page so I can... Here. So 15 is, we just did this one. We did this one.
Yeah.
This was 10. So what is this?
The horizontal shift of -1.
Of +1.
Oh, +1.
Which means to the right.
Yes, to the right.
So this is that curve right here.
From before.
Yeah, that was this one, number 9. She wasn't thinking very well when she put 15 and 9 on here. Or they weren't thinking very well. Yeah. So 19. 19. Where do we got to go to get 19? Up here?
I think that's back at the top again of
Yeah.
the first page.
Use the properties of logs. Okay. Again, pre-calc.
Which is something I need help with. I didn't.
What are the 3 most important properties of logs? Log of A times B is equal to what? The log of A plus the log of B. The log of A divided by B is the log of A minus the log of B. And the log of A raised to the B power is B times the log of A. So here's rule 1 pertaining to multiplication inside the argument, 2 pertaining to division, and 3 pertains to exponentiation. So they're giving us the log of 2 and they're giving us the log of 3 and they're asking about the log of 6. Well, first of all, I can say that the log of 6 is equal to the log of 2 times 3, which is equal to the log of 2 plus the log of 3.
And since they give you what 2 and 3 are, you just add those 2 together.
Exactly. So that's the name of this game on these problems. So let's do the next one. Which one? 21? So the log of 24, the natural log of 24.
So for 24, we do...
Break it up into products. Is there any products, or can you find 3 factors of 24 that are 2 and 3? All of them?
2 times 3 times is 6, and then times 2, and then times 2 again. So that's 4 factors.
Exactly.
Yeah.
So what's that going to become?
That's just the log of 2 times 3 added to the log of 3.
Right. Well, it's not the log of 2 times 3.
Well, yeah, but
it's the log of 2. Okay, you're right. It is the log of 2 times 3. Another way I could think of this would be, that would be the log of 2 cubed. And we're allowed to take that exponent and put it down there. So it really is the log of 2 times 3 plus the log of 3. Notice how I changed it to that? In other words, that's the same as the log of 2 times 2 times 2 times 3.
That makes sense.
Okay.
You're allowed to do that.
21. Next section. Use the properties of logs to expand it. Just expanding the expression.
So then for 21, that's ln of x minus ln of 4.
Yeah. I'm shocked because this book is the harder of my calculus books. And yet it spends so much time on pre-calc here. Stuff that really should have been learned in Algebra 2 or pre-calc. This is exactly the same stuff I'm doing with all my Algebra 2 students right now, and of course pre-calc students. No different. So, okay, so that's what that first one is, 21. was interesting to see the official math definition of log. The log of x is the area under the curve from 0 to x of 1 over t, dt. In other words, the official definition of log is, oh no, that's natural log, excuse me. The official definition of natural log is an integral, whereas I always thought that it was just the counter half of an exponential expression.
I didn't know that.
Well, I didn't know this until I reread that chapter today, that this is the official mathematical definition of the log of x. It's the area under the curve from 0 to x of this hyperbolic function, 1 over t.
That's interesting.
Yeah. Well, we know that that is the antiderivative of 1 over t. So, all right, let's see. We're supposed to do all the odds here. So what's the log of xy over z?
You just do ln of x plus ln of y minus ln of z?
Yeah. Or ln of x plus ln of y minus ln.
Minus ln of z.
Yeah. Yeah, exactly. 25 is a little different.
So, I guess
First thing I would do would be to write it without the radical sign.
Yeah, put the x squared plus 5 to the 1/2.
Mm-hmm. The reason is because it's much easier to work with exponents than it is radical signs, especially in logs.
And then break that into 2 additions.
Okay.
And the second addition is times 1/2.
Like that.
Yeah.
The one thing you got to be a little careful about when you're working with logs is that you don't confuse these 3 rules with addition, subtraction going on inside the argument. In other words, it's real easy to make this mistake.
To break it up.
And it's not true. In other words, the log of a times b is equal to that. We don't know what the log of a plus b is. We have no way to compress that or expand it. The log of a plus b is just the log of a plus b. That does not change to anything else. Okay? So the only thing you're looking for to expand is if multiplication or division or exponentiation is going on in the argument.
Okay.
Okay?
That, I want to say that'll be easy to remember, but I can see myself tripping up on accident.
Well, yeah, it is easy to accidentally trip up on it. That's why I mentioned it. Okay, 27.
So, I'd pull the 1/2 out in front, but do you then have 1/2 ln of x minus 1 minus ln of 1/2?
You can pull
1/2 ln.
Yes, you can. It gives you the same answer whether you pull that exponent down first or last, as long as you remember to carry forth the 1/2. However, it's a little easier to see if I change this to this. In other words, that is the same as that, right? Square root of a over b is the same as the square root of a over the square root of b.
Yeah.
Now, huh?
Yeah, okay.
Now I can use the division aspect to make natural log of that minus natural log of this. Then I can bring down the exponents. so that there's no confusion at all. Like that. Which is the same, if you think about it, it's the same thing as if I pull it down first and get rid of it here, and then I use division. I just got to make sure that that half doesn't get lost in the second expression. You know what I mean?
Yeah.
So if you're going to do it this way, then you want to do it like this. Put parentheses around that, like that.
Okay.
And then when you distribute the 1/2, you get the same thing that I got doing it the other way. But it can be a little confusing if you bring that 1/2 down first, because then you're not sure whether to distribute it to both terms or just one or whatever. What did we just do? We just did 27. 29, you know how to do.
Yeah.
30 is kind of interesting.
The ln of 1 minus, or 1 divided by e.
Yeah.
Which then breaks into the ln of 1 minus e, and the ln of 1 is log of 0?
Log? Yes, they're always 0, no matter what it is. Whether it's natural log or common log or log base 17. Logs of 1 is 0, always. Remember, logs are exponents. Any number taken to a 0 exponent is equal to 1. So all logs of 1 are 0. What's the log of e?
The log of...
the natural log of e.
I think that's 1.
It is. So our answer is minus 1. Okay? Our answer is minus 1, and notice there was actually a little maybe easier way to get to it. If I write it as the log of e to the minus 1, now that allows me to bring the minus 1 down in front, and I'm left with that. Since that's 1, that's my answer. So here we are compressing. We were expanding in that last set of exercises. Here we're compressing. So compress that into one log statement.
ln x minus 2 times x plus 2.
Divided by x plus 2.
Oh, divided, yeah, sorry. Oops.
Because it's subtraction.
Yeah. I don't know how I... Yeah.
This is how slide rules used to work. You probably have never seen a slide rule, but I had to get it when I went to mines. I had to buy it, and what you do is you multiply numbers by moving your rule, and the slide rule has nothing but log scales on it. So when you add 2 logs, it's the same as multiplication. So if I want to multiply a 3-digit number by a 4-digit number, I'll take the log of the 3-digit number, add it to the log of the 4-digit number, and then find that. It's pretty cool, actually, how slide rules used to work before calculators came along. So how about 33?
So, I would say we would combine that as the ln of x to the 3rd squared times the ln of, times x squared minus, all over x squared minus 1, and then the whole thing is to the 1/3.
Okay. I can also distribute that 1/3, and it might make it a little clearer. Notice that if I distribute it, I'm going to get the same answer that you got. but it might be a little easier to understand. Whoops. What are we doing? 33?
Yeah.
By distributing it, now I can take it and make it exponents immediately.
Which is much less confusing than what I just did.
I think it is. I don't know. It's easy to lose sight of. Were these all plus? No, this was a minus here.
The way I did it, I could have easily have forgotten the whole thing.
Yeah, it's easy to forget that 1/3. So now, putting everything in a signal argument, we got x plus 3 to the 2/3 times x to the 1/3 divided by x squared minus 1 to the 1/3. Makes me think that the better answer than that is to leave that squared and take the whole thing to the 1/3. Like that. And it might actually even be simplifiable more. In other words, we might find that when we expand this and multiply it by x, that maybe x squared minus 1 will be a factor of it. In other words, this could reduce. We'll not spend our time trying to see if that does reduce, because that's just algebra.
Okay.
Okay. So 35.
We have the log of 3 squared divided by x over 2 plus 1 to the 1/2.
Yeah.
Although, would that be easier to... I don't know, I was going to say, would that be easier to do to just solve the natural log of 3 times 2 and then...
Well, what we definitely can do is make it that.
Is make it 9?
Yeah, and I suspect that's the answer in the book. Do you have?
I do have the answers for this.
Can you turn to that page? I have in the back of my book also, but actually I'm not positive my exercises are the same. So why don't you look in the back of your book and see, it might be useful to know how far they simplify these.
This was 35?
Yeah.
For 35, they got that, the 9 over x squared plus 1 to the 1/2. Well, they have it, the square root of it, but...
Okay, and then in 33, is this what they gave as an answer?
For 33, they gave, yeah, that's what they gave.
Exactly this?
Let me check. Oh,
Or did they bring that 1/3 inside it?
Give me 1 second, my computer's freaking out.
Okay.
Okay. They have it written as the square root, the cubed root of all of that.
So in other words, they did this?
Yeah.
Really? Wow. Okay. Why would they do that? Why would they introduce radicals when you never want radicals? They didn't give us radicals. It's one thing if they'd have given us radicals. I could see them wanting it back in radical. But when they gave it to us as no radical signs anywhere, and then they put it in a radical sign, especially cube root, that surprises me. All right, let's see. What's next? 51. Ah, finally, calculus.
Find the derivative of ln of x to the 4th.
Use the chain rule and the power rule.
Derivative.
So y prime is equal to, if you're going to use the chain rule, the only thing you really need to know is what is the inside, right?
Would the inside for this be just the ln of x?
Yeah, in other words, if you were going to use substitution, this is what you would do, because then you'd have u to the 4th, and you can differentiate that quite nicely. So if you're ever confused about what the inside is and what the outside is, just figure out what you would make u if you were going to use u substitution. So the derivative of the outside is what?
4 u to the 3rd, but u is ln x.
What's the derivative of the inside?
The derivative of ln x, I'm not sure.
1 over x.
1 over x, that's what you do for natural log?
That's the derivative of the natural log, is 1 over x.
1 over x.
Which makes the integral of 1 over x equal natural log x. That's why that definition. Remember when I said the first time I learned the definition of natural log of x is actually the integral of 1 over x, or 1 over t from 0 to x, is the way they define it in your book. Okay. 57.
57. There it is. Are they asking us for the derivative of those still?
Uh-huh. So we have f of x equals natural log of x over x squared plus 1.
So then for this, would you break it apart and then take the derivative of the parts?
Well, yeah, we could do that. You don't need to do that. In other words, I can use the chain rule. I can take the derivative of the outside, which is 1 over x squared plus 1, times the derivative of the inside, but the derivative of the inside is a little messy. We got to use the quotient rule. This is even a little messy just because it looks funny. So I kind of like your technique of breaking it apart before we differentiate it.
So then it would break apart the ln of x minus the ln of x squared plus 1.
Yeah, and now that's not so hard to differentiate. So the derivative of that is...
That's just 1 over x.
And the derivative of this...
Is that just 1 over that whole thing?
It's 1 over x squared plus 1, but then I got to take the derivative of the inside also. Which is 2x. So there's our answer, which was much easier to get to the way you did it, by breaking it apart first.
So then I guess it kind of makes sense why they showed us all that in the beginning if they were doing this.
Yes, the whole beginning of the chapter was when you take a derivative of a complicated function, break it apart first, and it's much easier to take the derivative. But even better, let's say I have this. And I say take y prime. Well, you sure wouldn't want to have to use the product rule and the quotient rule, right?
Yeah.
I mean, that'd be a hard way to go. So the secret is you take the natural log of both sides. So now I have the natural log of y equals the natural log of that whole thing, and then I can break it down into natural log of x to the 6th minus 7 plus natural log of x cubed minus 1 minus 1/2 the natural log of x cubed. And now I can implicitly differentiate, and I have to implicitly differentiate in order to come up with y prime. In other words, my first step was to take the natural log of both sides. My second step is going to be now implicitly differentiate. Well, when I differentiate natural log of y, I get 1 over y dy dx when I'm implicitly differentiating it. Okay, now I'm going to be able to differentiate each of these separately quite easily. And dy dx will be equal to the derivative of each of those all times y. And that will give me dy dx. And y is equal to this. So I can go back and substitute for y if I want my dy dx to be all in x, which sometimes you do.
So using these natural log rules and all, you can easily, more easily do derivatives like that?
Yes. In other words, if you gave me this derivative to do, I don't even think I'd want to attempt to try to do that using the product and quotient rule. I'd either go crazy or make a mistake. But by taking the natural log of both sides, it's not going to give you a simple answer, but it's going to give you a quicker answer. It's going to be much easier to come up to the solution. The key is this. The key is the left side, because it's not real clear how you get y prime out of this. In other words, once you've taken the natural log of both sides, the only way to get y prime is to implicitly differentiate it, and when you implicitly differentiate it, that's what is left on the left. And there's your dy dx, and we're going to solve for that.
Yeah, okay, that makes sense. Yeah. That would have been nice to know last year.
Well, yeah, I don't know. I've never really seen a log problem that requires you to do it like that. I just saw it in a book where if you had a problem that was that complicated, it would be easier to do with logs than it would be normal.
I didn't have one quite that bad, but on a couple of our tests, well, basically all of our tests last year, he gave us extra credit problems that looked like that, basically.
Yeah, okay.
Assuming if we had extra time, you know, we could sit there and work through that whole thing, but it would have been a whole lot easier to do that instead of trying to work through those whole things.
Now, when your function is a log function, you don't need to do all that stuff. In other words, 57, I don't need to do it implicitly. 57, I have f of x equals natural log. Well, let's go ahead and break it apart. So that's equal to y. And now y prime I can take direct. I don't have to implicitly differentiate. I don't have to take the natural log of both sides first. So y prime is going to be 1 over x, the derivative of that, minus 1 over, oh, we did this one.
Yeah, and then that's times.
Sorry. Forgot what we had done. Next one is 61. Oh yeah, here they always love these. Love natural logs of natural logs. Let's apply the chain rule.
So,
in other words, there's no multiplication going on. There's no division. So there's no way I can expand that to make it easier to differentiate. Okay? In other words, this is not multiplication. This is not log times x squared. This is like a function. It's natural log of x squared. Okay, so I'm going to use the chain rule. We'll start from the outside. Y prime equals,
So then 1 over ln x squared.
okay, times the derivative of the inside. So
Which
if
is,
y were equal to natural log x squared, what would this y prime be?
so now we have, that's 1 over x squared, right? But then you have to take that times x, the derivative of x squared, so
Times 2x, yeah.
So,
Or,
yeah, so 2x
let's
over
make
1 over
this read 2 natural log of x, and then it's just 2 over x.
x.
Okay? So I want to multiply this by 2 over x. So this should be my answer. Do you have the page open to the answers?
Yes, I do.
What do they got for 61?
They have 1 over x ln x.
Ah, that's because this 2,
Yeah.
I can
Comes
put
out.
it in front, and then the 2's cancel. Yeah, always got to think about that. Logs always reduce more than I'm used to reducing them. So, all right, 69.
We have the log of the absolute value of sine x, or the natural log of the absolute value of sine x.
Let's talk about that absolute value for a moment. We can't take logs of negative numbers. So sine x half the time is negative. So that's why they put the absolute value in there. Now, don't think it makes a difference when you're differentiating it. What's this going to be?
Does that... I want to say it turns into 1 over sine x, but...
Well, not
Yeah.
1 over sine x, because you still got to take the derivative of the inside.
Oh, yeah, so then it's
Cosine x.
cosine x over...
That whole thing is cotangent x. Now, the only thing that I'm not sure of is what happens to those absolute values, and I don't think anything. I think the answer is cotangent x.
They got 69, they got cotangent x.
Just that? No absolute value sign?
No.
Okay.
So that absolute value sign's just there to trip you up, it looks like?
No, it's always there whenever something can be positive or negative. Notice that if I had x squared, the book mentions this, I don't need the absolute value because x squared is always positive. But if I ever have a function that is the argument of my log and it can ever be negative, I got to put absolute value there because otherwise I'm going to violate my domain half the time in this function.
So we're trying to demonstrate to you that if you have an absolute value, then you just do it normally.
Yeah. Let me think for a moment. So they're saying the slope of the curve is cotangent x. Okay, which is sometimes positive, sometimes negative, just like the slope of sine x. In other words, well, I don't even know what that graph looks like, so I won't attempt to graph it. But yeah, all right, let's go on. So I guess what we learned is that ignore the absolute value sign in a problem like this. What was that, 69? We need to do 77. Okay.
77.
Now, this might look hard because it says find the equation of a tangent line, but it's not. In other words, the equation of a tangent line is y equal mx plus b, right? It's a linear equation.
Yeah.
And the slope, m, is going to be the first derivative evaluated at that point. In other words, the point 1.
Yeah, these are
Okay, so let's keep that in mind. So let's find out what the slope is of this function. Let's make it f of x. In other words, if f of x equals 3x squared minus natural log of x, well, first of all, what's f prime of x equal?
6x minus 1 over x.
And what is f prime at 1 equal to?
F prime at 1, so then do we put the
Plug it
3
into,
in for x?
plug in 1
Plug
into
in 1
the
here.
into the derivative.
That's just 6 minus 1, which is 5.
Okay, so f prime of 1 is 5. That means our slope is 5. So we know this much. Y equals 5x plus b is the equation of that line. We need b. Well, how do we get b? Let's plug that point in for y and x. In other words, 3 equals 5 plus b. So b equals minus 2. So the equation of our line is y equals 5x minus 2. This is almost the quintessential question of derivative calculus. If you could be given one question only on a test of differential calculus, it would be find the equation of the tangent line to this function at this point. Because you have to know that the equation of the tangent line is a linear function that has a slope of m, and slope is the first derivative. So, and then using the whole point, we can figure out what b is. All right, so let's do another one of these for sure. 83. So 83 has different instructions. I hate to do a different one. Let's go back and do one more of those, even though she didn't ask you to do it. I want to make sure you can do that. Let's do 81.
81, which is f of x equals negative x squared ln x.
No, my 81.
Oh, sorry.
My 81 looks like that.
Oh, sorry. Couldn't see it. I was sitting back in my chair.
Okay. Now notice that the equation of the tangent line wouldn't make sense if you didn't specify a point, right? Yeah. Okay. So, in other words, we know we want to end up with y equal mx plus b, an equation where we have m and b. So first step is what?
Take the derivative, which would be 3x squared times 1.
Hold on.
Or 3x
Make sure
squared
that
over x.
No. You take the derivative of this times the other plus the derivative of the other times this. In other words, this is the product rule.
Product rule.
So it's
I forgot about that.
we don't do anything to natural log x yet.
And then it's 1 over x times x to the third. So x to the third over x.
So that's 3x squared natural log x plus x squared. So that's f prime of x. How do we find our slope?
Then we put in 1 for x, and we
in which equation?
solve it.
So
into
we want
the derivative.
Right. So we want f prime of 1.
Back. Yeah.
Well, what is that?
Which
log of 1 is 0.
So that's just 1.
Mm-hmm. Now we know our slope. So we know y equals x plus b. How do we solve for b?
For b, we put in the y value, or we put the derivative. We put in the slope in.
We put in both the y, we put in the y and the x value.
So then we just,
0 equals 1 plus b,
so
b
that's
is minus 1. So now the equation is y equals x minus 1. Such a simple equation for such a complicated function. All right, good. You know how to...
Yeah.
Since that's such a common question, I wanted to make sure you could do it after I explained how. 83. Here they want us to implicitly differentiate, not come up with the equation of the tangent line, but just implicitly differentiate. This is actually quite easy to implicitly differentiate. Implicit differentiation is a piece of cake. You just have to remember one thing.
To put in the dy dx?
If we are trying to find dy dx, then if we run into a variable different than x, we have to follow it by d of that variable over dx. So, let's start. That's,
so 2x.
I could even say that we have to follow even the x's by dx, but this is going to be dx dx, which is 1, so I don't need to write it. Okay.
And then we go minus 3 over y dy dx.
We're going to use y prime.
Okay. Plus 2y y prime equals 0.
Okay. Now what? Remember, we're trying to solve for y prime.
So move the x to the other side, the 2x to the other side, and then.
Now here's the tricky part. I need to solve for y prime now.
Pull the y prime out of both of those, and then divide the whole thing by y prime.
Exactly. In other words, factor the y prime out. So now y prime is going to be equal to that, all divided by this. And in this case, we don't care if y is part of the answer.
Yeah.
In other words, when you implicitly differentiate, you frequently get a function that has both x and y in it. Now, there are times where you have to go back and resubstitute what y is. We know what y is. What number are we on?
83.
Well, we don't know what y is. We can't really solve that for y. So we're going to have to leave the answer as a function of x and y. Do you have the page open that gives answers? Is this what their answer looks like? It might not look exactly like that, but it should look something like that.
Or their answer for, this is 83, right?
Yeah.
They have 2xy over 3 minus 2y squared.
Right. And the way they get that is by adding the denominator with a common denominator. Yeah. So that's going to become y squared over y. Inverting this, multiplying it, I get 2xy all over 2y squared minus 3. Is that what you read? No, you said 3 minus 2y squared, which takes away that negative sign. If I reverse that into 3 minus 2y squared, yeah, that's the answer right there. All right. Good. That was a good session on logs and derivatives of logs.
Thank you.
And I will talk to you next Saturday.
Talk to you next Saturday.
All right, Chase. Bye-bye.